Hello, and welcome to Chapter P, Section 5. Today we're dealing with exponential and log functions. Not really so much the graphing part. I need you to know what they look like, but I don't need you to actually graph them. So, real quick recap of what the graphs look like. So here we have the exponential graph of the equation y equals 3 to the x power, and I just chose 3 because it's my favorite number. And then for the log graph, we have y equals log base 3 of x. And hopefully you remember these two are inverses of each other. So if you reflect either of these graphs over the line y equals x, you would get the other one. And so in general, our exponential graphs always have a horizontal asymptote. So for example, this one, y equals 3 to the x power, has a horizontal asymptote at y equals 0. And then log graphs have vertical asymptotes. So this one, y equals log base 3 of x, has a vertical asymptote at x equals 0. So exponentials, always horizontal asymptotes. Log graphs, always vertical. In general, anytime our equations are going to look kind of like this, like if we have whatever number or even e to the x power, if there's something being subtracted from the x in the exponent spot, or even if there's something being added at the end, that's how our general equations are going to look like all the time. For logs, if we're dealing with either log or the natural log, so ln of x, and maybe an h in there if we have something being added or subtracted to the x, and then a plus k at the end for if there's something added or subtracted at the end. But those are like the general forms of what your equations are going to look like. So what I really need you to do is not actually to graph them. I just need you to know where the asymptotes are. That's the most important thing I would need. So in general, when we're dealing with the exponential graph, because it's a horizontal asymptote this way, the thing that'll shift that horizontal asymptote is that plus k at the end of the equation. So if something is being added to our exponential graphs, that's what's going to shift the graph up and down, which shifts the horizontal asymptote. But then in a log graph, what shifts it, if we have a vertical asymptote, then in order for it to shift, the entire graph would have to move side to side. And what shifts it there is the h value. And it's always the opposite of what it says inside the parentheses. So if it says like -5 or whatever, then it's moving right 5 instead of left, even though it seems like negative would move left. Okay, so that's the number that'll affect the asymptotes. So once you know where the asymptotes are, then you should be able to state the domain and range. So let's say, for example, we had the equation y equals e to the x plus 3 minus 5. Okay, so that would basically give us a graph that looks like the exponential one, so a curve like this, but then the plus 3 here would make it shift left 3 because it's next to the x, and then do the opposite sign. So left 3 and then down 5 for the -5 at the end of the equation. So if we took our entire curve, shifted it left 3, down 5, the horizontal asymptote would really just shift down 5, because if you had a horizontal asymptote that shifted left and right, it doesn't really change where the horizontal asymptote is. So its domain then is still going to be all real numbers, because we're looking at x values, and it looks like there's x values all over. You can use any x value for this graph. It extends forever to the left and to the right. But when we look at the range, really there's nothing that's going to be below the -5 because of that horizontal asymptote. So from -5, but not including the -5, since the graph will never touch a horizontal asymptote, and it goes upwards forever, since we're talking about y values for the range. Okay, so there's a domain and range for that one. Let me do one more example, this time with a log graph. So let's say I had natural log of x plus 3 minus 5 like this. So this time our graph's going to look like the log one, and same shifts here. We have a +3 next to the x, so this will move the entire graph left 3 to the left, and then down 5. But if our horizontal, or if our asymptote is vertical, if we shift it left 3, that's what changes it. If we go up and down, it doesn't change the position of the asymptote at all. So here, for our domain, because we have that break at the vertical asymptote, then really our graph will start at the -3, since our entire graph shifted left 3, but then it'll go forever towards the right, so infinity. And then the range, it goes up and down forever, so -infinity to infinity here. Okay, so that's all I want to talk about in terms of domain and range of our graphs. So again, I don't particularly want you to graph things, I just need you to know where the asymptotes are. So the other thing I want to mention are the properties of logs. So I know you started doing these in Algebra 2, then you did them again in pre-calculus. So now we want to make sure you remember them because we're going to use them a lot in calculus. So the properties, there are 3. We want to make sure that if you have logs, either a natural log or a regular log, of 2 things being multiplied together, then you can actually split them up into 2 logs that are being added. Or if we have a log where we see things being divided, this can be split up into a log or 2 logs that are being subtracted. And lastly, the last property is if we have a log where there's an exponent in it, we can split this up into the exponent being multiplied to the log. So with these properties, we want to be able to expand and condense logs. So what I mean by that is if we wanted to expand, we just want to rewrite them with as many logs as possible. So let's say I had natural log of 5 square root 3x plus 2. Well, here I have 2 things being multiplied. I have this 5 being multiplied by this big square root of 3x plus 2. So I can rewrite this as natural log of 5 plus natural log of the square root of 3x plus 2 because of property number 1, since they're being multiplied. Well then, I can actually still do more with this because a square root is really just raising something to the half power. So I can rewrite this as 3x plus 2 raised to the half power, because half power just means this is a square root. Oops. So now, since I have an exponent in it, I can rewrite using property number 3. So this will now look like natural log of 5 plus the half times the natural log of 3x plus 2. And that's the most I can expand this into. Another example is if I had natural log of x squared plus 3 squared all over x cubed. I'm trying to make this one look as complicated as possible. We've got craziness. So here we go, expanding this into as many logs as possible. I'm going to start with the whole dividing thing. So I've got natural log of x squared plus 3 squared, and this is being divided by natural log of x cubed square root x squared plus 1. Okay, so I just turned that division into subtraction. And then I've got an exponent in this first one, so I'm going to move that exponent to the front. So now this is x squared plus 3. And then with my second log here, I've got this x cubed being multiplied by the square root of x squared plus 1. So I'm going to rewrite this using a parentheses here, because originally both of these things were being divided. So with these 2 things being multiplied, this only applies to this log right here. So I just want to keep all these things within parentheses for now. Then from here, let's simplify this a little bit. So I've got 2 natural log of x squared plus 3. And this x squared plus 3 I can't do anything with anymore because I can't split up the 3 from everything because we don't have a property where it's not logs but still adding. So that has to stay like that. But then here I can distribute my negative into the 2 logs here. And this also makes sense because now both of those things originally were being divided, and so that's why both of those things need a negative sign in front. And then I'm just going to turn those into exponents and move those exponents to the front now. So this x cubed will now become 3 natural log x. And then this square root is really just raised to the half power. So this is minus 1/2 natural log of x squared plus 1. And that's fully expanded now. Yay! Okay, let's try one where we condense then. So condense means at the end you should only end up with 1 log. So if I have, let's say I started with 1/2 times the natural log of 4x plus 1 plus natural log of 5x minus natural log of 8 minus natural log, minus 1/3 natural log of x. Okay, so we got a lot of stuff going on here. Let me move those 1/2 and that 1/3 in front, and let's turn them into exponents first. So 1/2 turned into an exponent would just be 4x plus 1 raised to the 1/2 power, which remember is just a radical, plus natural log 5x minus natural log 8 minus natural log of x to the 1/3 power. Okay, let me rewrite these with radicals then. And so the 1/3 power would just turn into a cube root of x. Okay, then here we have 2 logs being added, so we can turn that into multiplying. So this would just be 5x times radical 4x plus 1. And then we have that minus natural log 8 minus natural log cube root of x. And so if I'm dividing, really that's just, if I'm subtracting, really that's just dividing. So this will now become natural log 5x of 4x plus 1 over 8. And then we just have one more log to take care of. So if I'm going to divide this one with this one, since we have the subtraction again, this just ends up being another division, or ends up being in the denominator. Okay, so my final answer here, we just have 1 natural log, and so the rest of it is all condensed. Okay, then the last thing I want to be able to do is solve these equations. So these equations will either have exponents or logs. So we're trying to solve exponential or log equations. So first one, let's say we have 7 equals 1/3 e to the x plus 1 power. So remember, our goal is to get x by itself. So first thing I want to do is get rid of that 1/3. So let's multiply both sides by 3. That way we can cancel out with the 1/3. So that'll give me 21 equals e to the x plus 1 power. And x is, if we want to isolate x, then since it's in the exponent, we got to get rid of that e. The thing that cancels out e's is a natural log. So if I take a natural log of both sides, then that'll cancel out with the e, leaving me with the x plus 1. Natural log of 21 is some decimal. I'm not sure what it is right now, but I'll figure that out later. And then I just want to subtract 1 from that. So make sure here that you're actually finding the natural log of 21 first before you subtract the 1, because it's not going to end up being natural log of 20. Because natural log of 21 is 3.0445. And subtracting 1 from that gives us 2.0445. And that'll be x. Okay. Not too crazy. Let's try a log equation. So let's say we started out with natural log of 2x minus 3 equals 5. Okay, so in order to get x by itself, we need to get rid of that natural log. So the thing that'll cancel out with it is e. So e we have to use as like a base. So we're going to raise e to the power of natural log 2x minus 3. And then on the other side, we'll do e to the 5th power. So it always has to be a power. You're not just multiplying. But that'll cancel out with the natural log. And then 2x minus 3 will just equal whatever e to the 5th power is. Looks like it's going to be 148.413. Okay, from here, this is super easy to finish up. So just add 3 to both sides, divide by 2. And we end up with 75.707. Cool. When you're dealing with log equations, one thing you have to look out for is when you plug your answer back in, do you end up with a negative inside the log? So this only applies to log equations because we have restrictions on the domain when we're dealing with log graphs. Earlier when we talked about it, there's always that like vertical asymptote with log graphs. So sometimes your x whatever you get for x doesn't work. So that's why we have to check. So if we were to plug in our x equals 75.707 back into our original equation where we were doing natural log of 2x minus 3, that 2x minus 3 part, you just have to make sure it isn't a negative number. And in this case, it isn't. So for log equations, you always want to plug your answer back into the original to make sure you're not taking a log of a negative number. Okay, and then one more example to do then. So last one. Let's say we have log base 5 of x plus 4 equals 2 minus the log base 5 of x plus 1. I wanted to do this one because we got 2 logs in it, so obviously much more fun and exciting. So if you ever have 2 logs, this is where the whole condensing comes into play because we don't want 2 logs. That's too much to deal with, duh. So if I can condense them together, then I'll only end up with 1. So what I'm going to do is move one of the logs over to the other side. That way I have logs on one side and numbers on the other. So I'm going to add log base 5 of x plus 1 over to the left. And now because I have 2 logs that are being added together, I can just multiply this. So this will end up being log base 5 of x plus 4 times x plus 1. All of that equals 2. Okay. If we have something in log form, we want to rewrite this into exponential form. That way we no longer have the logs. Or if you want to think about it as raising both sides to the base of 5 so that it'll cancel out with the log here. That's the other way to do it, but exponential form is the same. So you end up with 5 squared equals x plus 4 times x plus 1. 5 squared is really just 25, and then I'm going to FOIL out my x plus 4 and x plus 1 to get x squared plus 5x plus 4. From here, this is just a quadratic equation. I'm going to solve for x by setting it equal to 0, and then either factoring or using the quadratic formula from here. But I think this one doesn't factor. So let's use quadratic formula. Okay, so using the quadratic formula, I got it down to 2 decimals. So after I found everything in radical form, I just plugged it into the calculator to find my 2 decimals. So I got 2.72 and negative 7.72. So because we started with logs in this equation, we want to make sure that we don't end up with taking the log of a negative number. So if I were to plug in 2.72 into this first log part, log base 5 of x plus 4, I end up with a positive number when I do x plus 4. Same thing with the x plus 1. So the 2.72 should be fine. Cool. But if I look at this negative 7.72 that I got, when I add 4 to it for this first log, I end up with a negative number, which is bad. That's not allowed. So that means the negative 7.72 is an extraneous solution. So the only one that worked is going to be the 2.72. And that's it. That's it for solving log equations. Okay, guys, thanks for watching. Bye.